Welcome to the session on dynamic analysis in 3DEC. This is Jim Hazard, 3DEC product manager here at ITASCA. So we've already showed how the calculation scheme in 3DEC is an explicit scheme, which means that information propagates through the system. This makes it relatively easy to do a dynamic analysis within 3DEC. So if I just read the bullet points here, 3DEC simulates the full nonlinear response of a system to excitation from an external, for example, an earthquake source, or an internal, for example, blasting source. And reproduce evolution of permanent movements due to yield. The things we need to worry about in dynamics that we did not worry about so far are the following: wave propagation, boundary conditions. So we have different types of boundary conditions when we do a dynamic analysis. Damping. And then the last point is something specific to 3DEC called partial mass density scaling. So first, wave propagation. In an infinite isotropic elastic uniform material, we have two types of waves: shear waves and shear waves, also called S waves, and compressional waves, also called P waves. You probably are familiar with this already. Any study of earthquakes will yield a study of P waves and S waves. What makes it interesting, of course, is that when these waves encounter boundaries, you get reflections and sometimes refractions, depending on the contrast at the boundary. So the best thing to do here is to just start up 3DEC and look at a simple example. This is a one-dimensional wave propagation example. So we're going to make a 50-meter high sample. We're going to set it up so that the shear wave velocity is 1,000 meters per second. And you can see there's an equation here. The shear wave velocity is just the square root of the shear modulus divided by density. So we can choose the shear modulus and density to give us a shear wave speed of 1,000 meters per second. And what we'll do is we'll apply an X motion at the bottom, and we'll see a shear wave propagating up through the model. And then we can do all kinds of things like look at the effect of different surfaces and damping and boundary conditions and so on. So I'll just escape out of this PowerPoint and start 3DEC. Okay, I'm going to open an existing project. And this is a project that I've given you that you can download with the materials for this course. So if you look in the training materials that you downloaded, there is a directory called Dynamics. And inside of that, there's a directory called Wave. And inside of that is the project wave.prj. You can open that. So rather than have you go along and type everything here, I've given you this data file. So we can just walk through it here. This is pretty much the simplest possible dynamic model you could make. We start with model new, like usual. What's new here is model configure dynamic. We haven't seen this before. This is necessary in 3DEC because it allots more space in terms of the memory. So what we need to do is record accelerations of things when we're doing dynamic analysis. For the pseudostatic analysis, we don't actually care about the acceleration. So this is necessary to store the extra data. It's also, when you say model configure dynamic, it automatically turns off the damping. So the damping goes to 0, and it automatically turns off the mass density scaling. So if you remember from previous sessions, we do this mass density scaling to try and quickly get to a steady state solution. In a dynamic analysis, you don't want to do that because that will potentially cause distortions of the waves. So when you say model configure dynamic, it turns off the damping and turns off the mass density scaling, and you get a true dynamic solution. Probably most of the time when you're doing these dynamic analyses, you want large strain off. You can imagine the effect of these waves is not a large strain effect. These are relatively small amplitudes. And if you're interested in wave propagation, you certainly don't need large strain. So here we're just creating a single brick that's 1 meter by 1 meter by 50 meters. We generate zone. In this case, we just make it elastic. And again, we give these properties to get a shear wave velocity of 1,000 meters per second. We're fixing the y direction of movement, and we're fixing the z direction of movement on basically all the grid points here. And so we only have x movement. Again, this is sort of a one-dimensional problem. We're going to shake the bottom in the x direction. The grid points can only move in the x direction, but it will propagate up in the z direction. We're going to apply essentially a modified sine wave to the bottom of the sample. We can have a quick look at the function if you like. I've given it to you here, wave.fish. There are different ways to apply boundary conditions in a dynamic analysis. Often you will use a fish function if it's something that you can write in terms of an equation, like a sine wave. Most of the time in real life, you'll have a table of values, and that table might represent an actual earthquake recording, velocities versus time, or accelerations versus time. And so generally you would use, you would apply a table history when you're applying the boundary conditions. In this case, it's just a sine wave, so we can use fish instead. And we'll take a quick look at it. So we have a function called wave. We need a frequency. This is just a global variable. And so what it's doing here is it says if the time is greater than 1 over the frequency, it's returning 0. Otherwise, it's calculating something, which here is a cosine 2 times pi times frequency times the time. You'll have a look at this in a minute to see what this wave actually looks like. Okay, so if you have a function or you have a table, you can apply the boundary conditions like this. Block, grid point, apply, velocity x, 1. So this is the velocity value, meters per second. Fish wave, so it's going to multiply the return value from this wave function times 1 to get the velocity. So if I put in here, and if I look at this wave function, it's essentially returning values between 0 and 1. Because I set the parameter wave equal to something, that is the return value for this function. So wave returns a value between 0 and 1. It's multiplied by this base velocity, which I told it to be 1. And it's doing this at position z0, so on the bottom. I'm recording some histories. So I'm recording a history of the x velocity on the bottom. I'm recording a history of the x velocity in the middle. And I'm recording a history of the x velocity at the top. And I'm also recording history of the actual time. And just to double check, I'm recording a history of the source input wave. This should be the same as the history of velocity at the bottom, because I'm applying a velocity x of 1 times the wave function to the bottom. These two histories should be the same. Now I give some cycle. Now I don't say model solve in this case because it will never solve. Remember, there's no damping. So if I apply a wave to the bottom, it's just going to keep on bouncing up and down and up and down. So I can't say model solve. I just need to give some number of cycles. It's also common to give a time. You could say model solve dynamic time, and you give some time. In this case, we'll just use cycles. So I can run this. It creates the model, cycles at 2,500 steps. It's very quick because there's only one block and maybe 100 zones in this thing. I can actually quickly look at what the model looks like. I've given it to you as plot of 1. It's just a plot of the blocks. And I'll also plot the velocity vectors on this plot. So you can see at this point in time, there's a movement towards the right. But this is what the model looks like. It's long and skinny. Interestingly, here, what you want to do is look at the histories. So here are the histories. In this example, I've given them names, so it's easy to identify them. This is the input wave. So you can see what's happening here is the wave is it's a sine wave, but it's sort of shifted. So it starts out kind of gradual, peaks up, goes back down to 0, and the rest is 0. And I'll explain why we have this shifted sine wave in a minute. Okay, so we've got this shifted sine wave as the source at the bottom. Halfway up, we record the sine wave again, passing by. And then at the top, what's interesting here is we get the same wave, but it's double in amplitude. So the top of this thing is a free surface. We did not apply any boundary conditions to the top. And what happens is when that wave hits the top, the amplitude doubles, and then it reflects back down again. And this is why earthquakes, of course, are dangerous, because when the earthquake gets to the surface of the Earth, you get this doubling effect of the amplitude, which is really what causes the damage. Now you can see the wave is now starting to come back down again. This is the middle. Remember, the green line is the middle part. So the wave is reflected off the top, and it's starting to come back down again. You will notice here it displays the time step. So 3.28854 E minus 5 is the time step. You can actually work out the time step yourself if you want to, based on the stiffness, the density, and the zone size. And I've given this to you in the slides. I won't go back to the slides now, but you can convince yourself that this time step reflects the equation that is given in terms of calculating the time step. Actually, yeah. Okay, let's go back to the slides for 1 minute. Okay, so here's that equation. The time step has to be the minimum of the zone size divided by the p wave velocity, where the p wave velocity is given by the square root of the bulk modulus plus 4/3 times the shear modulus over the density. So as we talked about before, small stiff zones will really determine the time step here. The other thing to point out is that zones should be chosen small enough to resolve the smallest wavelength. So imagine you had 4 zones per wavelength. You will barely be able to resolve that, that wave. If you have 1 zone per wavelength, obviously you can't resolve it at all. So the recommendation here is you want to have roughly 10 zones per wavelength. You can work out what the wavelength is here from the velocity divided by the frequency. So higher frequencies give you smaller wavelengths and so on. In our example, the wavelength, remember the shear wave velocity was 1,000, and we set a frequency to be 40 hertz. So the wavelength is 25. We want our zone size to be less than 2.5. In our example, we set the zone size to be 0.5, so you can see in the histories that the waves are resolved quite well. Right? There's no distortion. Everything propagates along nicely. Now the question is, what happens if you don't have enough zones per wavelength? So we can try that just for fun. We can go back to our data file, and we can change the frequency to, let's say 200. This should be borderline. Let's have a look. So now if we look at the histories, you will see, of course, the wave is narrower because it's a higher frequency. Here it is when it hits the middle. You can see a little bit of distortion here. They actually call this dispersion when you get some bleeding of the wave after the time it's supposed to arrive. Bounces off the top, this dispersion is getting worse. It comes back down again, the dispersion is getting worse. So you can see that as you increase the frequencies, you're losing the fidelity of the wave here because you just don't have enough zones per wavelength to resolve the to resolve it properly. And you can imagine if I make this frequency higher and higher, this gets worse and worse. So what you need to be careful of is that you have enough zones per wavelength. But the other thing you can do is to figure out the frequency of your waveform. So usually you don't have a nice sine wave like this with a known frequency. Usually you have some sort of earthquake record. So here's just an example on the slides. Imagine you have an actual earthquake record that looks like this. So this is velocity versus time. You've got some wiggly real life data here. You want to figure out what the frequency is, or at least what the dominant frequencies are, so you can figure out what zone size to use. If you put this into a table, there's actually a function, table.fft, which stands for fast Fourier transform. If you run the fast Fourier transform, you can then plot power. It dumps it into a different table, and this table is power versus frequency. And so what you can see is where the dominant frequencies are. In this case, anything above about 25 hertz, we don't care about because there's basically no power in that. Maybe 20, maybe you could even convince yourself 15. You want to make sure that your zones are small enough to be able to resolve these frequencies, at least probably up to about 25, and then you should be okay. If you have a lot of high frequencies in your waveform, you can actually do some filtering. There's a dynamic wizard plugin that comes with 3DEC, and I'm not going to go into that now, but it's certainly possible to run that plugin, import your wave, and do some filtering so that you take out some of the higher frequencies. This example here with the table.fft I've given to you in the material that you've downloaded. Feel free to open up that project and run it and have a look at it. I won't necessarily do that right now. Okay, the next thing to talk about is the boundaries. So we just saw in the example that when we have a free boundary, it doubles the velocity or acceleration. If that was a fixed boundary, it does not double the velocity. Obviously, the velocity would be 0 because it's fixed. But what happens is it bounces off and it reflects, so it actually changes direction. So we can just have a look at that, and then while we're doing that, we can try and answer a couple of questions. We know that with the free surface we have this doubling effect. Well, how far does that extend? How close to the surface do we see that doubling? What is the effect of internal boundaries between different material types? So the case of this free surface is an extreme case where we have rock touching air, but what if we have one type of rock touching another type of rock with different properties? Then what happens? And then the third question we can look at is what happens if we have material yielding? So we set this properties to be elastic. Imagine they weren't elastic and the wave had an amplitude that was high enough to cause something to yield. Then what happens? So we can see some interesting effects there too. And I've given you some examples related to this, but we can just run them and have a look at them. Change our frequency back to 40. Okay, now let's fix the top boundary here. So right now it's free. We didn't assign anything, so it's free. But we could fix it. We can say block, grid point, apply, vel x 0 range pause z 50. So we're fixing the x motion of the top boundary. So when that shear wave hits the top boundary, it's no longer a free surface. The velocity is fixed at 0. It's just going to reflect off of there and come back down again. So we can run this. look at the histories. So now you can see what happens. This source wave is the same. Halfway up is the same. The top, we don't see anything because we fixed it at 0. Now on the way back down, it's reversed. Right? You can see that the sign of the wave, because it reflected off the top, it changed sign and is coming back down again. So this is what happens with a fixed boundary. All right, let's go back to the not fixed boundary. So we can just comment that out. Just run this again to remind ourselves what happened. Right, so we have this doubling effect. And the question is, if I look at my sample, we know at the surface that it's doubled. You know, how far down do we see that doubling? You know, how far down do we need to be worried about it? And so what I've given you a data file here. We don't need to go into the details. It's running the same model, but what I've done is written a little fish function that stores the maximum velocity observed by every point. Sorry, the maximum x velocity observed by every point in the model. And then at the end, we can just plot that in a table. So here's a function that stores the maximum x velocity of each point. And then we cycle it, and then we just make a table so that we can plot it. So you can look at this in your own time and figure out what it's doing. But once we run this, we can actually plot the table on a chart, and I've given this to you as one of the plots. And so the plot is showing the z position, so 0 at the bottom and 50 at the top, and the maximum amplitude that we were storing. So most of them is 1. Right? We put in that sine wave with an amplitude of 1. Right at the very top, maximum amplitude is 2, because we know that it doubles. And you can see there's a pretty rapid drop-off in the maximum amplitude here. So this doubling effect does not extend very far, is the answer to the question. This is about a quarter of a wavelength or something like that, in terms of the distance that this doubling effect occurs. So really, it's just close to the surface that you need to worry about this. Okay, the next question is what happens when you have an internal boundary. So I've given you another data file. Again, this is the same. We're doing it slightly different here. We're using hexahedral elements. They're just a little bit nicer for doing wave propagation. We can use hexahedral elements in this case because it's a nice 6-sided block, and we can fill them up with hexes. As mentioned before, in general in 3DEC, it's not that easy because you don't have nice 6-sided blocks, but in this case, we can do it. And what we're doing is we're setting up 2 different materials. So the base material is the same as before, density 1000, shear modulus 1E9. But we're making a soft material on the top with a quarter of the bulk modulus, sorry, a quarter of the shear modulus, yeah, a quarter of the bulk modulus. So it's softer than the base material. And then everything else here is the same. So we can run this. And here's an example of how you do this solve with the time. I haven't clicked it yet because we'll run this file first. We can actually watch what happens. So if I go to my plot 01, so here's my model with stiff material at the bottom and soft material at the top. And I'm shaking the bottom, same as I did before. And we can just run a few steps here and see what happens. So let's say model cycle 100. Okay, so here's the x velocity. It's starting to shake the bottom. Remember this trick, if I hit the up arrow in the command line, it will just repeat the previous command. I can run another 100, run another 100. We haven't quite got to that boundary yet. Run another, oh, here we go, we hit the boundary. You can see the wave is distorted. Next. Okay, it's gone through the boundary. Oh, but now look what happens. We get a reflection coming back down again. So we hit the boundary, part of the wave goes through, part of the wave gets reflected. So if we cycle, let's just say model cycle another 1000. And let's have a look at the histories. So here it's interesting. Here's the source, same as before. The middle, we've actually got a little bit of an amplitude increase here. At the top, we get that doubling, but look, at the same time, we see this reflection. It bounced off the middle part and it's coming back down again. And then you start to get weird because then you have reflections and double reflections and so on. But you can see that when you have a contrast in stiffness or density, you can get these reflections. And part of the wave gets transmitted and part of the wave gets reflected.